We're at GoToMath.com looking at some application problems involving linear equations. Okay, so we got a couple different problems here to do within the 10 minutes, so we'll be moving right along. It says Zach over at the coffee company needs to blend $5 per pound coffee with $11 per pound coffee to purchase a blend that will sell for $8 per pound. So he's going to mix them up. How much of each should be used to produce 300 pounds of new blend? So this problem is going to be similar to the investment problem that we did earlier, actually. Okay, just to give you an idea. All right, so we got $5 per pound of coffee. We don't know how much of the $5 per pound of coffee. We don't know. All right, so we're going to say, so the units always help out. $5, right, per pound, so over pounds, say LB here, times the number of pounds, and we're going to let A be the amount, okay, of the $5 per pound. So if this is in pounds, all right, then you cancel your pounds out, and what are you left with? You're left with dollars. You see that? You're left with dollars. So it always helps to kind of look at the units that we're using here. But instead, the way we're going to do this is I'm just going to write this $5 times A. Right? This would be the amount of blend A, we'll say. Plus, okay, we want to mix it with the $11 per pound coffee. So $11, this is the rate, $11 per pound. Now, we don't know how much, but there's a relationship between this amount and the amount of the $11 per pound, and that relationship is going to be the total number of pounds here, 300 pounds of new blend, so 300 pounds, and if you subtracted off this amount right here, right, that would give us the amount of the $11 per pound. Does that make sense? Is equal to, now it's 300 pounds, and we want this stuff to sell for $8 per pound. So $8 per pound times 300 pounds. You see that? So we need to know how much for the amount that we need to mix the $5 blend, and how much of the amount, right, of the amount of the $11 per pound. Does that sound right? So we have an equation here involving only one variable, so we want to solve for A in this problem, and that's actually pretty easy to do at this point in your math career. So we have 11 times 300, and that's going to be 3,300, 3,300 minus 11A. So if you remember that investment problem that we did earlier, wanted to invest some money, this is much like it, and I said, hey, look, you know, you could use this for a lot of other things, and this is one of them. Okay, so we got 2,400 over on this side, and let's see, what do we got? We got 5 minus 11. 5 minus 11. Alright, so we're going to have 3300 minus 6a is equal to 2,400. And let's go ahead and take this 2,400 over to this side. And we'll take this 6a over here. How's that? Alright. And so now we have 3,300 minus 2,400. That's going to be 900. Okay, we better not skip any steps. So that's 900 equals 6a, and therefore A is equal to 900 over 6, which is going to be equal to, and that's probably not going to go in evenly. I'm not exactly sure. We're going to find, oh, it does. Okay, that's kind of a surprise. So what is this? This is pounds, remember? And I don't know, LB, say that's pounds. So in the we'll call this amount 1 here, right? This is for the $5 per pound. We're going to need 150 pounds, and well, that's kind of strange, because that means A2 is going to also be, who would have known? Well, that'd have to be 150, because 300 minus 150 is also 150. Isn't that interesting? So it's actually an even amount for the $5 pound and the $11 pound to get the you can always check this, make sure you did your algebra right? We can take, let's just do that real quick. 5 times, how much time we got? Not much time. 5 times 150 plus 11 times 150, that gives us 2,400. Yep. So there you go. Alright. Okay, well, let's move on to the next problem. Okay, so we got a kayak. It takes 1.3 times as long to go 5 miles up the White River than to return. If the kayak cruises at 5 miles per hour in still water, what is the rate of the current? Typical problem. Okay, typical problem. So we're going to have to move on pretty quick here on this problem. We're going to let x be the rate of the current. Okay, rate of the current. And going upstream, the rate upstream, we're going to let this be 5 minus x. You see, because in still water, right, it's 5 miles per hour. That's how fast we can go in still water, but then we got to subtract off the rate of the current. We'll just call that 5 minus x. That's upstream, and then 5 plus x would be going downstream. You see, this would be going downstream, the rate of the current plus how fast I can row. So that's going to be the rate going downstream. Alright, good enough. Okay. Yep. So we got the distance. Let's see, what is the rate of the current? So we're going to be using this guy again. Rate times, or distance is equal to rate times time. You see that? We're going to be using that once again. So we got the distance upstream is equal to the rate upstream times the time upstream. Okay, and the distance downstream is equal to the rate downstream times the time downstream. Okay, and let's go ahead and solve for time. What do we want to solve for here? The time upstream. Okay, we're going to do this. So we have we got the distance upstream. So here's our relationship. Rate upstream is going to be equal to 1.3 times time downstream. Okay, and that's just by manipulating these guys around right here. Okay, so what does it say? The kayak takes 1.3 times as long to go 5 miles up the White River.